So yes, today I'm going to give you a little tour on the work we've done so far on active learning. This slide deck is already uploaded onto SlideShare. Please excuse me if I turn my head because I'm on two monitors during the talk. Or we're on Twitter as well. If for fun, if you want to follow us on bucket list papers as well, the 100 papers you have to read before you die in comp chem and medicinal chemistry. And the other link there, COVID moonshot, is the real COVID moonshot, not Boris Johnson's moonshot. So today we're going to go over what is active learning, what is the problem statement, what we're trying to achieve. And what we're principally interested in joining on matched molecular pair analysis and regression forest models in a closed loop to design compounds from very, very few data points. So I'm going to go through some of the features of matched molecular pair analysis that we've not talked about before, assuming that you're already experts on matched molecular pair analysis, and then also discuss how our regression forest models are built as well, and then bring that together basically to then go through some slides at the end of actually the active learning system we tried to develop and some of the lessons. And by now you've probably already read at the bit at the bottom. So like many of you, I'm sure going around the industry at the moment, everybody wants to make fewer compounds and get to candidate drugs quicker, or to the agrochemical quicker, or to their materials quicker. And over the last 8 years, the statement there in bold is what we've heard an awful lot of time. Can you magic us new hits and leads for this brand new target of which there's very, very little data? So we've fleshed that out a little bit more. What are we trying to do? So can we take a small amount of data, but with all the data and the knowledge we've extracted from matched pair analysis and machine learning models, and build a closed loop system where this can actively select compounds to improve properties and importantly improve the machine learning models? So what we get out at the end is good lead compounds, a novelty out of that as well. Quite a big ask here. So to be clear, this isn't taking where we have a data set for a well-defined protein target where we might have 1,000, 2,000, 3,000 data points against compounds. This is of the order of starting with 10, 20, 30 compounds and data points and very little known about the target, which is very typically where people start off in drug discovery. Now, so far we've been augmenting the chemist, and you all know about this one. We're pretty good now at getting databases together and organizing the data. We're getting better at that. And the role of the chemist has changed over these, and it's much more about a decision maker now. And we've all been working on automated systems to help, or a minimum, organize this complexity of data and present this in useful ways and present options for the chemist, so they become much more of a decision maker, much more of a goal setter. Now we're also talking about the grey bar, where the data and the robot are now starting to work together to start making each other better. So what we have in Medchemica is in supplying the space for the gold rush, as it were, is built our technology around matched molecular pair analysis. And we have three principal tools that support the chemists and to already provide a degree of automation. And you can read those on the left. There's spot design, where the chemist can try their own ideas. So a chemist can generate ideas and they can go in the score and store hopper of good stuff. Things like rule design can take the knowledge from matched molecular pair analysis and generate 100, 200, 1,000 suggestions to go into the store. Permutative MMPA I'm going to come on to, but that's essentially an automated free Wilson permutator. But also out of our machine models that are explainable models, where you can see where they come from. With analysis of area, we can spot missing features, and this now has the potential to feed back in an automated loop to actually purposefully design compounds to improve the machine levels. There's a little note there, slide 27, we'll come back to that. The last bit out of that, out of the models, we also now have a wealth of information about toxophores as well. So we can additionally add into the hopper of score and store alerts as well. Then you do make and test, then the data goes back in and the system should refeed itself. going forward and improve as it goes along. So the goal of this one, can we just start with a very small number of compounds, very little data, but our wealth of knowledge from all of our other projects, and start to close this loop going forward. I'm not going to talk too much to this slide, but this is about essentially further lessons and augmenting the chemist. And the only point I want to make here is to point out the reference to look at, but what's critical to chemists is to understand what's working under the hood. And they like to see structures, and they like to see that things are audible, and go back to the original data is very, very important. So building that always into your system is quite important. And that's the joy of matched molecular pair analysis. You can get back to the match pairs and see where the original data comes from. I'm not going to go through match pair analysis. The critical thing I want to point out on here, and there's a set of slides here that are included in the slide share to make this a full reference material. We capture a high level of environment. So not just the chemical change methoxy to hydrogen here, but we can go out a radius of a number of bonds. And by standard, we go out to 4 bonds. It's this level 4 environment means you have quite a large fragment of the molecule. And what that means is that this automates the process of identifying that group and quantifying that quite well in a free Wilson analysis, which means when you come to make combinations of groups, it's effectively done the automation process for you, and you don't have to think about coding up scaffolds with R groups on. So this is one of the endpoints of this talk is that permutative MMPA has been quite successful. So I'll say that for the first time now. So in this example here, CH2OH, we group on the match pairs, diverse compounds. We take the delta change between the measured properties, so 3 pairs here. If you extrapolate further and have more data, like 69 pairs here, we can now start doing statistics on this. And with a decision tree, we can then define rules of medicinal chemistry, or rules of agrochemical design, rules of material design. And we've published on this, Andrew on the call, there's his reference down to it, so you can go off and read about the decision tree. But to start off, we set a very conservatively high barrier where we need 6 match pairs, 95% confidence to declare something a rule of medicinal chemistry. So very robust, very reliable changes, not just to increase potency, but ADMET as well. So the rule design system, you present this with a molecule and you say, I'd like to improve solubility and metabolism. It will suggest a set of compounds to you based on these rules. Now then, compare that to a generative system, which could generate lots and lots of compound possibilities. And the task is to actually then find compounds within that are close to the chemical matter you're working on. Because it's taken your input molecule, you're automatically starting close to where you are. And because you're taking data from pre-existing projects, this is the type of thing that chemists have done to improve properties of compounds. So it's another direction to coming into generating new ideas. What we don't often have a chance to talk about is all of the stats data that we get out and how we drill back to original data. There's always a link through the REST API to get the original pairs back. And inside those is a wealth of data, because you can look at the pairs and then potentially be selecting out compounds that are close to where you're working. There's a wealth of stat data capturing the number of pairs, ups and downs, and median data, standard deviation. So the exciting thing from an active learning system is that this has the possibility of doing quite large jumps here. For example, a T-butyl isoster that I have here that means you don't have to go through the intermediate compounds, as it were, and have a brainwave at the end of it. This is captured in an unsupervised fashion to get you directly there. But there's also this wealth of stats data that algorithms could use to help select compounds. I've put Darren Green's reference in there to a Turing test on molecular generators, where matched molecular pairs came out kind of, as it were, the winner. Again, what we don't often talk about, I've talked about rules, but we also have this exciting possibilities for active learning. We have a grouping that's all of the rules, irrespective of where they come from. It'll generate about 5,000 or 6,000 compounds. It's excellent to take the results for that and use them in docking studies as well. And getting scores out of those works really well, that does. We also have hit to lead as well, and I'll just quickly cover this science behind here. These are the most frequently performed medicinal chemistry changes. And what you do is you set a threshold over the number of pairs you have and extract those transformations, typically 250 pairs or higher. Sometimes we have to go low, 100. It depends what an organization has in their data set. If you look at those transformations, the name, as it's named, it's hit to lead. It tends to be the common things, putting methyl groups, chloro groups, methoxy groups, cyanodes, the common things that people do early on in a discovery program. So that's a quite exciting set for active learning. I mentioned we have quite a high threshold, 6 match pairs or more. We now can drop this threshold back and say, well, what are the transformations where we've got 3 or more pairs as well? And this will typically give 1,000, 2,000 suggestions. So we're dropping the statistical threshold, but we're going broader with more ideas that are relevant. In addition to that, by extracting the public data that's available out there, we can group those data sets together into classes depending on their proteins. So for example, dopamine here, we can group together all of the individual dopamine assays and say, here's a rule set for increasing potency for dopamines. Also works the other way. It's helped get me out of this dopamine. What would you do to kill dopamine activity for a specific target? But you can see here 3,548 rules for dopamines here. So we have the possibility of saying, if we've got a new dopamine target and all these other dopamines here, we can say what has worked with dopamines in the past that could generate us new ideas and new compounds. So exciting stuff there. I've mentioned permutative MMPA. This is the process of now dropping the threshold even lower just to every transformations in a smaller data set. And so what you're doing is you're permutating all of the different groups around your scaffolds. So you might have a transformation between M1, M2, M3, and M4. M2 and M4 don't look particularly special compounds. But if you apply that transformation now to compound M5, you might achieve the holy grail of reducing lipophilicity and increasing potency, getting you beyond that Pareto frontier. And as I mentioned, we can do this without the R group mapping. What's exciting as well, and in the world of very small data sets, potentially the first data could be coming out of patents. So you might have a little bit of internal data and a little bit of patent data. You can extract the transformations out of that and combine them together and generate new compounds out of that as well. Here's a real life example from a protein-protein interaction work that we did for a client. All the blue spots are existing compounds and data points, and by some cutoffs and thresholds, taking the estimated potency from this, because we can estimate that from the difference that we get for the transformation, and a C-log-P cutoff, we got 52 novel suggestions out of this one. So quite useful stuff. So that's the MMPA stuff, regression models. So quite simply, we built our system on a feature, a topological distance, and a second feature. And the classic things, acids, bases, hydrogen bond donors, acceptors, aromatic groups, hydrophobes. Once you have those 360 descriptors in place as a fingerprint, we can then use to build those models. We're often asked, do we incorporate C-log-P in molecular weight? And no, we don't, because we found we're double counting features by doing that. A couple of slides there for reference of where we got the descriptors from that are smarts based. It produces good models. Here's a slide to give you an example of, look at the right hand structure, a base, 2 atom links to an aromatic. You're a knowledgeable audience, you know all of that. The purpose of doing this was actually to avoid worrying too much about the quality of the actual prediction number, the actual how good is this number over here and what range it was. Because back to the start, what the chemist wanted designing compounds was to look at the features of the molecule. So when we present this to users for a prediction for a compound, we show in red the things that are contributing to binding. And in this particular case, red, well, you want to get out of the M1 receptor if you can, because it's a known toxophore. And you can see how that contribution is adding up to the sum of the potency prediction. And then also what features are helping you get you out of there. There's K and N along the bottom as well. So we do that as well. And presenting the two, the chemists understand where this comes from, and they can then make a judgment and a decision about how importantly they take this computation forward. Now, from an active learning point of view, this is quite interesting as well, because now we're going to ask a computer to do this. And of course, what's important in here, these are good models, but what we want to do is always optimize models. This is an analysis of error. So absolute error up the y-axis and measured value along the bottom. Our global mean error for the model is the line in green. And there are lots of things and lots of features for this particular data set we analyzed here. I can't remember which one it is. I think it's the Herd data set. There's lots of things we predict well. But there are many, many things that we don't, because there's not enough data. So here, because we can now identify these features, we could be programming this back in, and that was that dotted red line at the start, as an active learning system to start designing compounds. And this is what we call the explore method. So here we go, active learning. Let's bring this all together now. So can we use matched molecular pair analysis to generate the virtual compounds? Exciting, does the hit to lead transformations actually get us a good start? If we use some of the ADMET properties like metabolism and solubility, we're building those in from the start. Does that help us as well? Can we use target class transformation learning as well? And say like the dopamine set here to then also generate us ideas that increase potency and get us on a faster track as well. We have a regression forest models. We know with say 30 data points, they're not going to be good to start off with, but can we start to generate a feedback loop to then be synthesizing compounds that would reinforce that model, and so the errors reduce. Now, from the get-go, we started to think about strategy. How do we start this game going with different strategies? Well, there's an explore strategy. You've got to build up a little bit of SAR. Do you have to do that? I actually posed that as a question to the group. Do we have to do that? And later on, you'd think once you start to know things and the models become better, you're in exploit strategy. So you'd be targeting the high potency predicted compounds with the lowest error on them. And that would make sense driving towards a candidate drug. So schematically, where do we start? We have this small number of hits, and we're saying 30 in the first instance. And we can build a model with that one, and we can ask the matched molecular pair to generate some compounds. And in the hopper then, we say, specify which strategy we're going from, and we'll pull out in explore mode a diverse set of compounds, those with high error on them, because we want to kind of understand where things are. They're likely to fail, but we'll understand things. And then if we were in the real world and we were doing wet chemistry and biology, we'd start making the compounds. They would go into a criteria, and all the data would go back into the database to rebuild all the models going forward. So to set this up as a test to see where this is going, we took a larger data set, selected 30 compounds, and then the synthesis and test part, we then went to see if the compounds that came out of the red decision box were then in that test set. And if they were in that test set, we would declare them as made and then analyze the data again going round. So onto some data. So I reinforced that one. So we started with dopamine D2, and we selected 30-week active compounds out of this with some kind of randomness to it. And but because not truly random, because we'd selected quite a tough criteria of being weekly active. And then the rest of the data set, the 5,200, we could then look up as the potentially made set of compounds. And so it doesn't produce a great model to start off with. So when you then run these 30 compounds through the matched molecular pair analysis with hit to lead, the dopamine class, solubility, metabolism, you can see the number of compounds generated here out of the system. When we then take these compounds, it was remarkable how few of them actually matched against the 5,200 data set. But it did actually, we did actually do some potency predictions out of this one, and we did actually see some real data that matched up against. One of the more interesting ones was, to our surprise, despite the fact that Permutative MMPA with our environment size set as 4 only said, how about making these 5 compounds next? Guess what? 3 of those were made. And that's one of the kind of resounding things that came immediately out of this, was actually the Permutative MMPA was quite good. Now, you're a knowledgeable audience, you're probably going, yeah, that's right, isn't that? Yeah, it is. There's clearly that, if you think about it, that was going to work. And this is effectively what happened. You identified the transformation of actually, with quite small molecules here, from methoxy to a hydroxy at the bottom. So that's what it looks encoded with an environment level 4 on it in blue. And then if you mutate this compound here to at the bottom left into this compound, we actually predicted 6.1 out of this computer is actually 7.9. So there's actually a boosting additive effect on that one. So that looked really, really exciting and looked really good. And we thought we're onto something here. We are a little bit disappointed that the matched molecules didn't hit more compounds. But then to our surprise, as we started to loop this, it got stuck. And we couldn't, as it were, break out. And the reason is because such a small match is against the literature compounds. Now, it's a difficult experiment in terms of building this virtually, because we might simply be victims of what's published. And so whilst there's lots of good suggestions in our system coming out, that's not necessarily what people have actually written up and published in a paper where we can actually get the data set out for it. Potentially lots of early useful SAR compounds where you've eliminated certain functional groups because they drop activity, the so-called activity cliffs, are not included in papers. So we would have had more matches that potentially could have improved our model. So essentially, we had to think there's got to be a loading phase at the front. So the second variation of this was then to think about the front end and go, well, let's make sure we've permed things, do the permutations. Let's make sure we've done all the pattern data. Let's make sure we do really, really simple things and do an induction phase where there does, without doubt, need to be a first 50, 80, maybe even 100 compounds made and 100 data points measured for us to actually then build something that's significant. Then that sounds like we're not achieving the goal of what we're going to do, but you have to start somewhere and learn somewhere. And then once you've got that, then join it actually into the loop. Now then, I alluded at the start of all these possibilities of data sets and different types of runs we could do with matched molecular pair analysis. I haven't talked about going down to the 3-pair trans variants as well, and we've not done that yet. There's various other possibilities and thresholds. There's various ways we can analyze the stats data and get more information. There's various ways that we could drill into the pairs themselves to find things that are similar. In other words, there's an awful lot of possibilities and data that goes into us. And whilst we started with explore and exploit as two simple strategies, potentially there are innumerate numbers of strategies. And very quickly we started to think about chess. And you all know this, that about the first 8 moves in chess have all actually been permutated and are well understood on a lot of the effects they do. And you know that there's various defenses and positions you can take. And fairly early on in chess, you learn that you need to control the middle of the board. You can do those kind of permutations because at least at the end of the day, there's 64 squares on the board. But it does feel like that with the system getting stuck, that potentially it's almost like the same as humans. We can get stuck down an alley with a series and we can't break out of it. So potentially what's exciting is what is the new AI that's actually going to sit with this system that's part of the strategy selecting process. And maybe will it always need a human intervention there? Will always need 10 human interventions there? Question, can you actually have an AI system follow projects and follow the work that they do and start to build up knowledge about different strategies going forward? This has left us with a lot of open questions, which is pretty exciting, actually. So there we go. I'll just wrap up now with some summaries from that. The great thing is that the MMPA and regression forest models did work together, and we can join the loops back together and start to suggest compounds. I've talked a lot about those strategies there, and I suspect there'll be more and more strategies. The initial phase with a small number of hits still remains a challenge, and will we have to do a different type of process there to generate a small deck of compounds that actually make sure we can break out in lots of different directions there, because this process can get stuck. What we did fundamentally learn out of this is just how much permutative MMPA works very well. So actually, we've poured our effort actually into completely automated permutative MMPA, and really working that into systems. And again, that becoming a system that's for the augmented chemistry. And I mentioned at the end has left you with some questions about can AI actually help with the compound selector and select strategies as well. As usual, there's a lot of people to thank. Throw all your criticisms at me and throw all of your praise at the people listed here. So I'm pleased to say Lauren Reed is about to start working with us again at Medchemica, having gone and finished her PhD. Jessica Stacey, who is talking next, did a lot of work. The pair of them did a lot of work on the early machine learning models. It's another talk. We did develop another system, and predictions were really good, but it was very easy to be out of domain. I'll leave that one hanging. It's excitement. Some great coders are Katie, Phil, and Shane, and of course you all know Ed and Andrew as well working on this. Thank you very much for listening as well. Just the last reminder, the slides are already on the slide share. You might have already downloaded them already. Happy to take questions.
Thank you very much for the talk, Al. We have 2 questions in the Q&A. The first one is from Michael Krug, and he asked, what is the difference of MMPA to a change of fingerprints, Morgan 4?
I'm sure you could do it with both. One of the useful things that we have out of the MMPA is it very explicitly captures the hydrogens atoms, and we encode all of those. I would have to go and look a lot at the Morgan fingerprints to see to what degree that could be done equivalent as well. Not a precise answer there, but an interesting question.
There are 2 more questions. Feel free to choose.
Oh, sorry. Yeah, sorry. I'm still on full screen, so I can't see the.
The second one is from, how could you improve handling of non-additivity of SARs in active learning?
Yes, absolutely. So that again, that is going to be, as another person in the field said to me, it's all great when the stars align, basically, and these things add up again, but when they don't, this is tricky, basically. So yeah, I think the only way we can do that is actually gather the data and work our way through that. And it'd be like I perceive it as any other kind of piece of cheminformatics kind of problem. We need a good set of examples to then actually start to think about how we'll deal with it algorithmically. But that is an absolute challenge. I think it is for the humans as well, having done that enough times on enough projects to go, oh, I don't understand why that didn't work. So yeah, what's the last question? Second one.
Oh, there are more questions. So
oh, good.
I will catch up with the remaining questions, but here is another one. Great talk. Can we imagine a strategy to select CPD with low, medium predicted potency with high error, but that will extend the applicability domain of the model for the next steps?
Yes. So this is what I was alluding to on our strategies were too straightforward, basically, and we could start to do exactly that. That's the right things to be experimenting with. What I'd ideally do with is of course the same thing that a lot of people want, which is a complete and full data set to work on, and then have a much higher chance of actually being able to work through these.